Hi, welcome to a series of lectures on machine translation with particular focus on the degeneracies of the problem of machine translation, as well as how we tackle this problem of machine translation using neural machine translation. I am Kyunghyun Cho. I am an associate professor of computer science and data science at New York University, and also a senior director of frontier research at the precision design team within Genentech. So let's talk about machine translation first. What is machine translation? And in particular, what is what we call neural machine translation? Human language is fascinating, and it is fascinating because of its richness and complexity. For instance, you're looking at one of my favorite passages, that is the final passage from the novel 100 Years of Solitude by Gabriel Garcia Marquez. And if you notice, this is not even a paragraph. It's just a single sentence that just talks about how the whole novel wraps up. And the fact that we can actually write such idea into a sentence with such richness and complexity just tells us about how awesome our language is. Now, our goal is to translate such a complex idea encoded in natural language, in fact, in one language, into the equivalent sentence in another language. There is a problem of translation. If you think about it very naively, you can view yourself as either a professional, if you are one, or amateur linguist, and then try to imagine what goes on in our head when we try to translate a sentence we have just seen in English into another language that you may be more familiar with. In my case, that's going to be Korean. And often our mind goes into this process that is often called analysis, transfer, and synthesis. So we start from the source sentence. We're going to try to figure out what each of the words in this source sentence means. And then given those words in the sentence, we're going to try to figure out how they are composed, both syntactically and semantically. And then once we have done the analysis, we eventually get to the meaning representation of this source sentence. Now, what do we do from there? We're going to now start putting in little by little the structures coming out of the target language. We're going to add in the semantics, we're going to add in the syntax, we're going to add in some of the words, and then eventually we end up with the target text that is a translation of the original source sentence. Now, this is what we often think of what happens in our head when we try to translate text. However, there is another perspective into what translation is, and then that's more of a mathematician's perspective. This actually does have a very long history that is more than half a century long. In 1949, in the memorandum titled Translation, Warren Weaver wrote, "It is very tempting to say that a book written in Chinese is simply a book written in English, which was coded into the Chinese code. If we have useful methods for solving almost any cryptographic problem, may not be that with proper interpretation, we already have useful methods for translation." In this perspective, a source sentence that needs to be translated is simply a string of symbols that expresses what was already expressed in the target language, which is yet again a string of symbols, except that these symbols are very much specific to the target language. So then translation is simply to try to decode out the original meaning, that is a target sequence of symbols, given the source sequence of symbols. So this is very much the mathematical perspective into what translation is. And this is the perspective that we're going to stick to in this presentation, as well as the one after. So from this perspective, the source sentence is really just a sequence of tokens. And then each and every such tokens in this sequence is from a finite set of unique tokens, which we often refer as a vocabulary. Now, considering this, we now see that there are exponentially many possible source sentences with respect to the length or the maximum length of the source sequence that we allow. Then what is a target sentence? Now you get it already, right? It's just another sequence of tokens. And often the tokens in the target sequence come from a different finite set of unique tokens, which we're going to call as a target vocabulary if needed, or just a vocabulary unless there is absolute necessity for us to distinguish between source and target vocabularies. Of course, it's very, very much possible that these vocabularies, source and target ones, do overlap significantly. Just like in the case of the source language, there are exponentially many possible target sentences with respect to the maximum length that we allow. Now, once we have established how we're going to represent source and target sentences or text snippets as a sequences of tokens coming out of the finite-sized vocabularies, then the goal of translation becomes to figure out what kind of algorithm we can write in order to turn the source sequence into the corresponding target sequence while maintaining the meaning as closely as possible. Obviously, one thing we are sure is that we don't know how to write that algorithm, because even people who speak multiple languages, they don't know how they do so. They don't know how they understand a sentence they hear or read in one language, becomes some kind of abstract notion of meaning in their head, and then when they say it out loud in another language, how that actually becomes the actual, let's say, speech or the written text that they write. So we really don't know how to write it down because we somehow do it, but we don't know how to do it. So instead, what we do is we're going to take the approach based on machine learning, where we're trying to learn, or we want to come up with an algorithm that automatically learns to translate based on past translations. So we're going to collect all those data that records how a lot of the source sentences were translated into corresponding translations by often human translators in the past, and using that data, to which we often refer as paracorpus, we are going to come up with a machine learning algorithm that learns to translate from a source sentence into a target sentence. Now, one way to think about translation in this machine learning perspective is that translation is more or less scoring. There are exponentially many possible target sequences or the sentences, and then our goal is to, given a source sentence, let's try to score each and every one of these target sentences and pick the one that has the high score. Now, unfortunately, this is not really the most reasonable or the obvious approach to take, just because there are just so many possible translations. We cannot imagine scoring each and every one of them separately and then choose the one that has the high score. It is just not going to work. So what we then do is to try to bring the notion of probability in order for us to come up with a way that is more efficient than trying to score each and every target sentence independently from each other. So what do you mean by bringing the notion of the probability? We are simply saying that the scores that are assigned to all the translations are going to sum to 1, and each and every one of those scores is a number that is between 0 and 1. Now, given this, what we need to do is to make sure that the higher probability, that is number closer to 1, is assigned to a more reasonable or plausible translation given a source sentence. It's just like what I just said. So what changes by using probabilities instead of scores that are not really restricted in this particular way? It turned out that we actually know quite a lot about probability and statistics, and then we can use our knowledge of probability and statistics to come up with a more efficient way to compute the scores as well as to estimate these scores from a large-scale parallel corpus. So then what are those the tools or the knowledge that we can use? One thing we know is that we can rewrite the probability over many variables, so many tokens in the target sentence, by write it as a product of a smaller probabilities assigned over smaller units, individual tokens. Now, one thing we have to be careful is that we cannot really assume that the probability assigned to each and every word or the token is independent of the probabilities assigned to other tokens or just of the other tokens. Just doesn't make any sense. Why is that the case? Because it turned out that there are very strong dependencies among all those tokens in a target sequence. And then that's what makes natural language processing as well as machine translation fascinating. We have a sequence of tokens, and then the choice of a particular token in the middle of the sequence is heavily dependent upon the choices that we made for other locations within sequence. And what this actually means is that there could be many different ways to create valid translations or the sequences that have the same or the very similar meaning. So here's one example. This is a sentence I took away from The Tale of the Fortunate Rope Maker by Ted Chiang. The sentence is, he stepped through the gate of years to see the Cairo of 20 years later. Now, let's consider these two possible translations. In the first one, I know that there should be 3 words followed by Cairo를, followed by 4 words, followed by 문을, followed by 1 word, and a period. Cairo를 means Cairo. 문을 means gate or door. Now in the second translation, I can have 3 words followed by 통과해, which means step through, followed by 2 words, followed by Cairo를, followed by 1 word, and period. And then what was the meaning of the Cairo를? That was just Cairo. And then we see that the choice of where to put this word Cairo를 can change depending on which words or which token I decided to put in other locations in the sequence. And the interesting thing is, once fully completed, both of these translations are perfect on themselves. So we could have chosen either of these without any issue, nor losing any of the meanings. So what that means is that we have to somehow rewrite this probability that we assign to a sequence of target tokens given the source sentence in a way that's going to be both efficiently computable and also preserves these strong dependencies among all these tokens. When it comes to capturing these strong statistical dependencies, there are 2 ways to go about in machine learning. The first one is autoregressive modeling, where we write the probability over all these variables that correspond to target tokens given X as the product of conditional probabilities of predicting the next token given all the previous tokens. Now, second approach is the latent variable modeling. Instead of considering only the target token variables y1 to yly, we introduced another variable that is hidden. So we never actually see the value of this particular variable. So we call them hidden variables z. Now, what this z does is to capture all these statistical dependencies or to capture a particular choice of the tokens in different locations. Once we try all possible values of z and then compute the average score assigned to the actual observed translation given that particular configuration of z, we suddenly end up with the distribution over this translation that capture or that has strong statistical dependencies among all those target token variables. Just because of my training, I do prefer the latent variable modeling. However, it turned out in the case of machine translation or general natural language generation, the first approach, the autoregressive modeling, has been found to be exceptionally effective. And that's the paradigm we're going to stick to today for these two lectures. Now, in autoregressive modeling, let's just review it once more. What we do is, instead of computing the probability for the entire sequence at once, we try to compute the conditional probability of each and every token given all the previous tokens. So this given all the previous token part, that part is where we actually introduce all these dependencies. So in order to know how good the choice of any particular word is, let's say YT, we need to know what kind of words were selected from Y1 to YT minus 1. And this is where the statistical dependencies come in. More intuitively, or the more in a graphical format, what we see is that we have as many, we have all these random variables that correspond to target tokens, as well as the random variable that corresponds to a source X. And we can now show or illustrate the dependencies modeled in this autoregressive modeling by drawing an arrow from all the previous tokens as well as the source sentence into the next token variable. And then we do that for every single one of them. It actually agrees quite well with our intuition on how the surface form of language is produced. We read source sentence, and then we're going to produce one word at a time in the translation until we complete this translation of the source sentence. A very nice property of such autoregressive modeling is that it makes the problem very challenging problem of machine translation, where we need to be able to assign high probability to one or very few of the exponentially many possible translations into a supervised learning problem. And then how does that happen? Now, what do we have at the time of learning? We have a parallel corpus that consists of all the past translations, all the source sentences from the past, and then how they were translated. That's what we have in a parallel corpus. Then how we train this neural machine translation system or any kind of machine translation system is to ensure that this system, P theta, is going to assign high probability to the translation of a source sentence within this parallel corpus. And then this is what we often refer to as maximum likelihood learning. And then however many examples we have in this parallel corpus, we're simply going to say that we have to make our machine or to train our model to put as high probability as possible on the translations that are paired with the source sentences in this parallel corpus. And the interesting thing is, this is where the power of the probability or the probabilistic framework comes in, is that because these are probabilities, they have to sum to 1. What that means is, if I increase the probability of a correct translation from the parallel corpus, it automatically decreases the probabilities of all the other possible translations given the source sentence. It just falls naturally out of having this constraint or having this score as probability, that the probabilities have to sum to 1. Now, let's get back to what I meant by it just becomes a text classification. Because we use the autoregressive paradigm, we rewrote the probability of Y, the translation given the source sentence, as a product of probability of each and every token given all the previous ones or the preceding ones. And because we work often in the log space, we always prefer log over the probability. In this log space, log probability of a sequence becomes the sum of the log probability of predicting the next word given all the previous words as well as the source. And what that means is that you can view this as trying to classify the source sentence concatenated with the prefix of translation. So what has been translated so far into one of the as many categories as there are tokens in the vocabulary, target vocabulary. So it's really just a classification. Given some text snippet, source sentence, and then the prefix of the translation, we ask our model to classify or to categorize into one of V many categories where the V corresponds to the size of the vocabulary. And one thing we have learned over the past about 10 years now is that we know how to train this very large-scale neural network for text classification. We can use transformers, we can use recurrent networks, we can use convolutional networks, or we can use any combination of these, and then we know how to build this text classification. Now, of course, there are some issues with it, but we're going to talk about it much more in the second part of this lecture. But this is precisely what we have done over the past, let's say, 7 to 8 years in the field of machine translation. And in fact, statistical machine translation has been continuing to improve ever since it was introduced in 1989 by a team at IBM back then. And then the animation that you're seeing on the top right corner of the screen is the animation released from the Google Translate showing how many languages they are covering and how that has been improving and how much better the quality of translation system for each of the language got better over, how much better it got over the years. And it's quite impressive. In fact, my mom really started to use Google Translate in order to read my blog posts in English using Korean, and she's now able to actually tell me about what she saw and what she thought about my blog post. So that's really impressive. It wasn't imaginable for that kind of thing to happen 10 years ago, because 10 years ago, the best we could do with the Google Translate or any kind of machine translation system was to make fun of it, right? But not anymore these days. And then, of course, with a lot of caveats, we started to see so-called human parity, at least in a particular domain of news articles or other restricted domain. And then what do we mean by a human parity? Is that for some set of articles or the documents, we often cannot tell the difference between the translation created by machine translation system and the translation created by human, sometimes even professional translators. there are a number of conditions that need to be met for this kind of human parity to be observed, but these conditions are becoming less and less important. In fact, already in 2019, at WMT's Shared Task on News Translation, we did observe that in particular language pair directions, such as German to English, English German, and English to Russian, the best performing systems that were submitted to the shared task achieved human parity. Although for many other language pairs and directions, we still have some way to go. So then is the problem of machine translation as well as natural language generation solved? That's clearly not the case. And as scientists and engineers, our job is not to be too excited by the advances that we see in the field, but rather our job is to figure out what are the things that are still need to be done. What are the things that have not been done well? What are the things that people have forgotten to look into? And then trying to figure out what those are, characterize them, and then try to come up with not the solution, but come up with solutions to address those issues. And today, my lectures are all about these issues. And in the first part, this part, I'm going to talk a bit about the indeterminacy in machine translation. And this kind of, let's say, goes together with the why we still need the human translators. And also, what are the things that need to be done better in machine translation? Let me just play one video clip for you that I actually created. So the Papago or the Naver Papago is like the Google Translate in Korea, run by Naver, that is the largest tech company in Korea, if I recall correctly. And then their translation system works quite well. And sometimes my mom or dad use Naver Papago in order to translate my blog posts or some of the news articles that they see on the internet. Now I opened the Papago, I set it to translate from Spanish to English, and then I decided to just type some random stuff. As you can see on the screen, as I add the letter A over and over to the source side, the English translation just wildly fluctuates. Sometimes a bit understandable, it translates into ah. Sometimes it's going to say with a flap, whatever that even means in this context. And sometimes it just says something completely different. What if I write D's instead of A's? Well, it's actually outputting some Korean as well, not even English. And then as I add more and more D's, apparently I get something different. Something is definitely not right here, as you can see. Well, apparently Naver Papago thinks that it's none of my business, and I don't know where that comes from. Pat Sandlot, what is this? Wave, Pat Sandlot, wave. Let's look at just one more thing. I'm going to just write F over and over. The power of the head, muff, 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 muff. I don't know. I'm at the and muff, maybe. How about E? Ouch. Okay, makes sense. Ace. Okay. E. Maybe that's okay. Oops. Who knows? Maybe okay. Oops with the exclamation mark. Okay, and so on. And goodbye. Now this is really weird, right? And then perhaps some might think that okay, that was too weird. Maybe this is just some, let's say, weird thing that happens with a particular combination of Spanish to English. So I decided to, okay, let's try then Korean to English. Why not? Because after all, the Naver Papago is known to work really well between Korean and English, as well as Korean and Japanese. So on the Korean side, I decided to just type some random stuff that doesn't make any sense. Those are not even a well-formed syllables to start with. But somehow the Papago started to just apologize over and over, nonstop. And sometimes it just revert to some random stuff on the target side. Perhaps because the input was random, maybe that's what we expected it to see, but it's unclear. So what is going on here? Let's think about it a bit, and then we can think about what is actually happening here from some of the assumptions that we make in training these machine translation systems. So what do we mean by training, or what do we actually want to do when we train a machine translation system to do translation? Well, I guess what we want to do is for the machine translation system, this MT system, to consider all possible pairs of source and translation. So all possible pairs of the source sentences and target sentences. And then only if those are very likely, we want our system to put a very high probability on the particular pair. So that is, we're going to look at all possible source sentences, but we're going to weight them according to how likely they are. If those source sentences are very, very likely, very well formed, we're going to consider them more. If they're very unlikely, we're not going to consider them enough. Now, given that likely source sentence, we're going to look at all possible translations. And those translations that are very, very likely, that is, that are good translations, we're going to ask our MT system to put high probability on that likely translation. That's what we want to do. And this is what we call expected risk minimization. So we want to look at the all possible cases, look at what kind of risk or the loss we can expect, and then we want to minimize it. Unfortunately, this is impossible. Why is it impossible? Because there are just so many possible source sentences and target sentences to the point that considering all possible combinations just does not make any sense. So what we do is we are going to rely on the sample-based estimation of this expected risk, and we call it empirical risk. So we draw samples from this source distribution. So we're going to look at many source sentences that are very likely, statistically very likely. And then given each one of them, we're going to draw at least one reasonable translation according to a distribution. And all these examples are drawn independently from an identical true distribution. That's where the IID assumption comes in. And then once that happens, what we say is that these are all reasonable source translation pairs. So our system should assign high probabilities to all these pairs. And this is precisely what we do in order to build the machine translation systems, as you have learned in this winter school, as well as you have seen in any papers that you have seen about machine translation, as well as natural language generation. And we know how to do it very well. And then we know quite well when it works, how it works, and how well it should work as well. Now, unfortunately, this assumption of IID, in particular the identical distribution assumption, is a bit problematic because it assumes that our system is going to work well on the source sentences that were drawn or that are likely under the distribution, the source distribution P star of X, that were used to draw source sentences during the training time. Now, what happens is that the things change, the word changes, the language that we use changes. What that means is that the very likely source sentence 20 years ago may not be likely 20 years later. Very likely source sentence now may not have been very likely 20 years ago when we trained or when we collected this parallel corpus. What that means is that we probably cannot expect our MT system to well behave on a so-called out-of-distribution source sentence that is inevitable. Source sentences or the language distribution is dynamic. It's never static. It changes over time. And then unfortunately, the way in which we train these machine translation systems do not allow us to expect it to behave well on all possible source sentences coming out of the current source sentence distribution. And some of the extreme examples are the ones that we saw. So when I typed many G's, and then told the Papago translator that it's in Spanish, of course, this having G's, repetition of G's is very, very unlikely under the source distribution that was used to train this MT system. And thereby, we cannot really expect it to behave well. And then, unsurprisingly, the translation it generated in English was mellow extreme. Absolutely, it has absolutely nothing to do with repeated G's in the source sentence. So what can we do? Perhaps the issue is that we just have to make sure that we use, or given a source sentence, we make sure that that sentence is indeed very likely source sentence under the source language that we consider. So for instance, if we ask the Google Translate to translate a repetition of dog, the English word, into English by forcing the model that the source sentence, this repetition of dogs, is in Maori, probably doesn't make any sense. Because in Maori, dog, 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 dog is not a likely source sentence. So perhaps what we can do is that we just do the source language detection. So given a source sentence, tell me in which language it's written down. And then we're going to suggest that, okay, it does not look like Maori. So do you want to try to translate from English? Maybe that's a way to go. Unfortunately, it turned out the source language detection itself suffers from the very same issue, because the language detector looks at likely sentences from all those different languages. So let's just look at how the Google Translate source language detection works. I set the source language as Hawaiian, started to write A repeatedly, and then at the bottom of the window, you see that you see the suggestion on the source language from Google Translate that is fluctuating across many different languages. At the moment, it says that these repeated A's is Telugu. I don't think that is the case. How about B? So initially, up to 3 Bs, it just says there's no suggestion, but from the 3 to 4 Bs, it's going to suggest that perhaps it's in English. And then having more and more Bs, it's getting stronger and stronger. It becomes more and more confident that it's English. Now let's see. Vietnamese, then English. That's weird. That's probably neither Vietnamese nor English. Now let's try D. What happens? No suggestion so far. Danish. Is it because it's D? Welsh. I'm pretty sure that it's not Welsh. And, briefly English, but then it came back. Now I started to type the first consonant in Korean. Oh, it says, we should translate from Korean. That makes a bit more sense, right? Now let's go with F. Romanian. And back to English. I don't know. Again, neither of them is an answer. So in some sense, we can say that the unexpected translation is expected when the source sentence was unexpected. That's a bit sad. So then perhaps what we can do is we do the so-called density estimation. We're going to train a language model that is not a translation model of the source sentence, so that this language model is going to tell us how likely the source sentence is. And then if our language model tells us that it's not likely, then we're going to simply say that the source sentence is not likely enough for our translation system to translate correctly or accurately. That sounds about right. This is what human translators would do. Unfortunately, it turned out that training such a language model is a very difficult problem. We're going to talk about it a bit more in the second part of this lecture. But it turned out that when we train this kind of language model, we do observe a lot of weird degeneracies, such as this language model saying that the shortest, as in empty sequences, are highly, highly likely under this model. And then we all know that the silence is gold, but that doesn't mean that the silence, no, let's say no word sentence is most likely. The issue with the people always is that we talk too much, not, we stay quiet. So then, of course, the one may ask a question, or the smart ones may ask a question that perhaps we can just look at this kind of uncertainty. So if the uncertainty output by our model is too high, we're going to simply give up on trusting the translation that we create. Now then, the issue here is that issues here include, first, how do we compute the uncertainty of this kind of structural prediction of machine translation system? There are some ongoing work there, but that's a bit out of the scope. The second thing is that let's say we can somehow have an algorithm that gives us the uncertainty estimate of any generated translation. How do we trust? How much trust should we have on this uncertainty estimate itself? So uncertainty is there to quantify how much we should trust about the actual answer, let's say y hat here, the translation, but then how much trust can we have on the uncertainty value itself? And then in order to think about it, we need to think about what it means for the uncertainty or probability to be meaningful, or sometimes we often say well-calibrated. And then the idea is that the probability of some event is well-calibrated if I look at historical record of that event happening, and then the frequency of that event happening, in fact, overlaps very well, or they agrees very well with the actual probability of the event. It's very frequentist view, but still, this would be a one reasonable way to measure how well calibrated the probability or the uncertainty estimate is. Now, unfortunately, we don't know how to compute that in this kind of very in the problem where the space is exponentially large. If there are only few, let's say classes in the case of the image classification problems and whatnot, what we can do is that we're going to really look for every possible event, that is every possible class, and then see how many examples, what kind of, let's say, probabilities we get for those classes, and then see if that's actually the frequency at which that class appears. But in the case of translation, we have so many translations. It's impossible to see how often that happens. I mean, the space of all possible translations is larger than the entire training set we have. Now, of course, we can't really just give up, right? That doesn't make any sense. So some people, in particular in the machine translation community, have been working on the problem of so-called quality estimation. If we have a separate set of examples for which we have a source, translation, and associated quality annotation given by the professional translators, can we build a quality estimation predictor in a supervised way? Now, this is very much specific to machine translation. However, this has been, in fact, studied quite intensively, and that this may be one way to figure out whether some translations are just so lower quality that we should just give up on providing it as an answer and just fall back to asking the professional human translators. Now, unfortunately, this is very, very difficult problem. You gotta collect a lot of data. And then, collecting a lot of data like this requires us to query all those professional translators who are quite busy people and expensive people as well. And furthermore, there's a question of whether we want to do the quality estimation separately, or should such annotation just be folded into training a machine translation system itself? Now, of course, at this point, you might actually ask a question whether it's that big of an issue, right? So, all the examples that I showed you were using nonsensical sentences. So perhaps, as long as we ensure that the no-nonsense users are only, we only serve the no-nonsense users, maybe that's fine. But it turned out that that's a bit of a naive perspective. Because hallucination, or it's kind of coming up with the crazy translation that may not have anything to do with the source sentence, is a necessary evil in machine translation or translation in general. Now, I took one sentence or sentence in Korean, 되돌려받지 못할 것이라 들었다. You see on the left-hand side. And then I went to both the neighbor's Papago translator and Google Translate. And then tried to translate this sentence into English. And I got two different answers. Naver Papago said that translation of 되돌려받지 못할 것이라 들었다 was, I heard you won't get it back. On the other hand, Google Translate said the translation should be, I was told that I would not be able to get it back. Now I can tell you that both of these are perfectly correct. However, when you look at the English translations, you notice that these are in fact two different sentences. They have two different meanings. Right? The first one says that I heard that you won't get it back. But the second translation by Google Translate says that I was told, so I heard that I would not be able to get it back. So these are clearly two different things. Some similarities, but clearly two different sentences. Now the reason is because of partial observability. So where does this difference come from? Partial observability. Our implicit assumption when we build this kind of machine translation system is that the source sentence is complete. That is, the source sentence or the source contains all the information needed for our system to translate it. However, in reality, this assumption almost never holds. There are so many variables that we do not or cannot observe. And then this unobserved variable, Z, induces uncertainty or the ambiguity. And then this ambiguity needs to be resolved somewhat arbitrarily. Let's look at an example. What is the thing that is not being observed here? According to the Papago's translation, it says that I'm hearing from my friend who's saying that I won't get it back. On the other hand, with the Google Translate, it says that I'm hearing from my friend that you won't get it back. And this ambiguity comes from the fact that the source sentence does not specify who's not going to get it back. Just due to the fact that the Korean is a project language, and then you can always easily drop verbs. So here, what is not being observed is who is not getting it back. Now, obviously, one might think that we just need to give more context. Maybe looking at the entire document is going to help us. Or perhaps we can go for multimodal machine translation where we give access. We give our machine translation system access to other modalities. For instance, we perhaps could provide images together or of the scenery in which the conversation is being made. Or we may be able to provide audio together with the text, perhaps. And indeed, when you go to Google Translate and give a bit more context, that is, 나는 매우 슬펐다. I was very sad. Then suddenly Google Translate fixes the translation by saying that I was told that I would not be able to get it back because I'm the one who is sad, right? Unfortunately, this is not really enough because the people have tried for the past, let's say, 6 to 7 years trying to build a document level machine translation, which has helped us quite a bit. But when we look at all these particular cases where we know that document level context should help, these document level translation systems do not exploit such document level context perfectly. It really works well, but still there are places where the human translators almost always get perfectly, but the machine translation systems just fail to do so, even with all the context that has been given. And the worst is that it's fine that the MT systems or the machine translation systems cannot resolve these ambiguities itself. I mean, that's fine. That's just because there are maybe just not enough information in the source sentence. So the source is incomplete. But the worst issue here is that these MT systems make an arbitrary choice. And then what kind of choice is made is not really controllable. If you recall, Naver Papago said, I heard you won't get it back. Google Translate said, I was told that I'll not be able to get it back. And then I had zero control in which one of them should be selected by my machine translation system. I just had to get whatever it says or whatever the arbitrary choice the machine translation system made. I didn't have any other option. That's the only thing that I could rely on. Because I know Korean, I can tell you that these two are different things, and then I know that both of them are perfectly correct in the context of these incomplete source sentences. But then if you don't know Korean, you can't really tell if there were other possible perfectly correct translations. And sometimes these arbitrary choices amplify undesirable social biases, which is kind of the thing that we want to avoid, but technically are very difficult to is very difficult to avoid, and then that kind of gives me nightmare every night. So then one might think about, can we then measure the level of this ambiguity or measure the uncertainty in our systems, let's say prediction, that is translation, and can we use it? It turned out that we can't really, we don't really know how to correctly compute this kind of entropy in a high dimensional space of our model, which is an imperfect proxy to the true ambiguity or the true distribution, which already has some ambiguity there. So it looks like it's a very difficult problem, and it needs to be tackled, but we don't know exactly what is the right way to tackle this problem. So we talked about two different indeterminacies in machine translation in the first part of this talk. We talked about the out of distribution short text, and we talked about the natural as well as the artificial ambiguities in translation. Unfortunately, these two indeterminacies or the two issues are not easily solvable, and then I don't really have good answer for you in terms of how to tackle these issues. And then these two issues may require us to even rethink of or to reformulate the whole problem of machine translation from scratch. And interesting thing is, human translators, in particular professional translators, are extremely robust to this kind of issues. And they also have luxury to interact with the people who ask them for translation as well. On the other hand, the systems that we're building do not have that luxury and also are pretty bad at even detecting that there exists such ambiguity or the issues in general. So still at the 2-0, humans are ahead of machines. So to wrap up the first part, machine translation has come a long way since 1950s and has made a tremendous progress. And then one way in which we have done so successfully is by looking at machine translation, the problem of machine translation, not from the domain-specific perspective, but from a more abstract mathematical perspective. And then the gap between translators and machine translation systems has significantly narrowed over the past, let's say, 10 years on average. However, this gap is becoming even more apparent as our systems get better, because we started to look at all these difficult corner cases, such as where the genuine ambiguities exist, as well as when the source sentences just are nonsensical. And this is why I'm here today, is to tell you about these issues, not only the solutions that we have come up with. We are all scientists and engineers. What we want to know about is the issues that are inherent in our systems so that we can characterize them and fix them. And then one way to do so, in particular when we build this kind of natural language processing systems, is to think of how you and I perform these tasks ourselves, because we are the experts in natural language. We are the ones who actually evolve the natural languages ourselves, and then try to use that intuition as well as the insight in order to come up with the better solutions. Now, of course, in the second part of this lecture, we're going to talk a bit about the thing that we know a bit better and for which we have at least a partial solution. Thank you. We'll be back in 10 minutes.